Alright, in this video we're going to begin our discussion and review of how we solve systems of equations. We're specifically going to focus on systems where we have two equations containing two variables. And the first technique that we're going to review is how we solve systems using graphing. It's relatively simple to solve a system of equations using graphing. When we have a system of equations, the way we solve it using graphing is we're just going to graph the two equations that are in the system, and we find the intersection point. Once we find the intersection point, that is the solution to the system. Just to make sure our graphs were correct and that our solution works, we can then check the solution by substituting it back into the system and making sure it makes both equations true. So for instance, I've already drawn a graph of a system here where we don't even know the equations, so we won't be able to check the solution, but we can find the solution to this system. We focus right here on this intersection point, and that point is the point 3, -2. And so that would be the solution to that system of equations, whatever those two equations are. Okay? Solving systems using graphing works best in one of two scenarios, although we can use it on any system, but it works best in these situations, either when we're provided with a graph, like we were here, we just had a graph of two lines, needed to find the intersection point to find the solution, or if we're given two equations that are in slope-intercept form, because they're easy and quick to graph. It keeps us from having to manipulate the equations. Like I said, we can solve any system using graphing, but these are when it's easiest and best. Alright, let's look at a couple of examples. First example here, we're going to solve the system y equals 2x minus 5, and y equals -1/2x plus 5 using graphing. So I'm going to start by graphing the line y equals 2x minus 5. It has a y-intercept of -5, so I count down to -5 on the y-axis. And it has a slope of 2. So from there I'm going to go up 2 and over 1 and plot another point, and up 2 and over 1 and plot another point. And then I have a bunch of points, and I'm going to connect those points with a line. And let's see. Use my ruler. It's especially important when we're solving systems by graphing that our lines are as accurate as possible, because we're looking for the points where these lines intersect. And if we're less than accurate with our graphing of the points, we're going to find solutions that are not correct. And now we're going to graph the second line, y equals -1/2x plus 5. It's got a y-intercept of +5. And a slope of -1/2, so I'm going to go down 1 and over 2 to the right, down 1 and over 2 to the right, and then I'm going to connect those points with a line. And let's see. And when I do that, I see that these two lines intersect right here at this point. That's the point 4, 3. And so 4, 3 is going to be our solution to this system. And now that we're done finding that, I'm going to go ahead and check that system, check that equation or that value in the system. If I put 3 in for y and 2 in for x, that should give me a true statement. 2 times 4 minus 5 should be 3. And it is, so it works in the first equation. I do the same thing in the second equation. I'm going to put 4 in for x. I've got -1/2. Oops, I'm going to put my fraction in parentheses here. -1/2 times 4 plus 5, and if it's correct, that would be 3. And it is, so it checks in both of the equations, and that is the solution to this system. Alright, let's look at the next example. In this example, we have one equation in slope-intercept and one that's not in slope-intercept. So we're going to have a little bit more work here. Like I said, there's no problem with us doing it. First, we're going to graph y equals negative 3x minus 3. Got a y-intercept of negative 3 and a slope of negative 3. So I'm going to go down 3 and over 1, down 3 and over 1. And then I'm going to draw my line. And then we're going to convert 2x plus 3y equals 12 into slope-intercept form in order to graph it. So we want to solve it for y. Subtract 2x from both sides. Divide both sides by 3. And make sure we divide everything on both sides by 3. And we get y equals negative 2/3 x plus 4. So we'll plot the y-intercept at 4. And the slope tells us go down 2 and over 3 to the right. Down 2 and over 3 to the right. And then I'm going to draw the line through those points. There we go. And the intersection point for these two lines is right here. And that's the point negative 3, comma 6. And now I want to test this in the two original equations. I put negative 3 in for x in the first equation. And make sure that it gives us 6. And it does. And in the second equation, I'm going to put both x and y values in the left-hand side of the original. 2 times negative 3 plus 3 times 6. And if this is correct, it should be 12. And it is. So our answer checks out. And that's the solution to that system. All right, one more example. We're going to graph y equals negative 2x plus 5. Solve this system by graphing y equals negative 2x plus 5 and 4x plus 2y equals negative 8. I'm going to graph this one first. It's got a y-intercept of 5, a slope of negative 2, so I'm going to go down 2 and over 1 to the right. Plot a couple of points. Break out my handy-dandy ruler and draw the line through those points. And then the other equation I need to turn into slope-intercept form in order to graph it. So I'm going to subtract 4x from both sides. And I'm going to divide both sides by 2. And then I'm going to plot the y-intercept at negative 4. And use the slope, go down 2 and over 1, down 2 and over 1. And draw the line through those points. And we have something interesting happen here. These two lines don't intersect. And it's not just that they don't intersect on our grid, they don't intersect at all. We should know that these two lines are parallel because they have the same slope. When we have two parallel lines in a system of equations, when we graph it, that means that there are no solutions to this system. There is no ordered pair that makes both of these equations true. Okay? Something else that could happen that you might see, we didn't do an example like this, but it's possible that when we graph the two lines from a system of equations, that they end up being the same line. We end up graphing them on top of one another. If that's the case, we'll say that there are infinitely many solutions to the system because any point that's on the line will be a solution to both of the equations. Those are some special cases that can occur, the parallel lines being no solutions and what we call coinciding lines leading to infinitely many solutions. Other than that, the majority of systems that you encounter when you graph them, you'll probably be looking at a situation where they intersect at one point, and that one point is the solution. All right, that wraps up our video on solving systems using graphing. We'll look at other system solving methods in a few of the future videos. See you next time.